Okay, Jomon, let's start.
Yes. So good afternoon, Dr. Biju, Senior Francis, Manoj Matthews, all the other professors and dear students. Once again, welcome back and very good afternoon. We had an very excellent class on Wednesday, and the concept is very clear. I mean, it was very clearly explained. Generally, in organic chemistry, students have a practice that they learn many things by heart, and that will be helpful in their examinations when the questions were direct, but that will never help to solve a problem in any of the competitive examinations. But now these things, aromaticity, cyclic reactions, you have to learn the concept, understand the concept is very important. And yes, partly in the last class we had very explained the concept very well. And that was an excellent class. And today we are the second class on that continuation. Will be, I think, it will be mainly focused to pericyclic reactions, and that is also another thing where you understand the concept very well to solve problems. It is not just by heard things. It will not help you in any of the exams. So we are expecting another wonderful session today, now in the coming 2 hours, and we will be concluding this topic, molecular orbital approach to organic chemistry, that session today. And hope and be sharing all these videos in YouTube with our students and even other colleges, and we just found that they are all feeling that these are very helpful for them, because and it can be used for their reference later also. So thank you, Professor Biju, for joining with us, and hope we can start now. Over to you, Dr. Biju.
Yeah. Thank you very much, Jomon. Good afternoon to all of you. Yeah. Can I share my slide?
Yes. Please.
So, is it visible?
Yes, it's visible.
Okay, good. Okay, so good afternoon to all of you once again. So I hope all of you remember what we discussed on Wednesday afternoon about a little bit about the MO concept, how the MO concept can be utilized for knowing some basic things about aromaticity. And we also saw some of the important transformations or some of the answers to the questions related to aromaticity. So we continue our discussion, especially on aromaticity, and we will start our discussion on another important topic where we can apply the knowledge of molecular orbital theory, or the concept of this come in various pericyclic reactions. So I hope you remember the MO diagrams of the organic compounds such as butadiene, and I also told you how you can extend this to 1,3,5-hexatriene, and also benzene, where the knowledge of this MO orbitals, molecular orbitals, how we can define the degeneracy, and we don't have to draw every time. With the knowledge of Frost circle, we can have a good feel about how many degenerate orbitals are there in a polygon with n centers, as like a hexagon, a pentagon. And we also saw a little bit about the aromaticity, anti-aromaticity, and also a little bit on non-aromatic compounds. So to continue where we stopped last day, so we also discussed some problems on aromaticity. So I will just continue from there where we stopped. So if we have two compounds, cycloheptadienone. So cyclopentadienone and cycloheptatrienone. And if you treat these compounds A and B separately with malononitrile, only one of the compound, say for example, A does not react with malononitrile, whereas B reacts with malononitrile to form an orange-red solid. So B, so this is otherwise industrially known as tropone. And this compound reacts with malononitrile in the presence of a base to form an orange-red solid, whereas cyclopentadienone does not react with dicyano or the malononitrile, no reaction. So any of you can tell what is the explanation, how this, how we can explain this? So for cyclopentadienone, it does not react with malononitrile, whereas tropone reacts with malononitrile. If you recall, we have discussed on Wednesday, cyclopentadienone reacts with acetone, whereas if you take cycloheptadienone or tropone, it does not react with acetone. So this reacts with acetone, reaction happens. Here there is no reaction. So it is something very similar to that question. So cyclopentadienone, when it treats with this malononitrile, there is no reaction, whereas tropone reacts forming an orange-red solid. Can you explain, any of you, why it's like that? Okay, so I will.
Yes, sir.
Yeah, please.
The ion generated from A is an anti-aromatic compound and which does not exist in nature. So that reaction does not happen.
So that is true with this one also, right? Cyclopentadiene. So the anion generated from cyclopentadiene, or the here you are talking about the anion from here, right? Or the other way around?
In A, the ion generated from is cyclopentadienyl cation.
Okay.
Which is anti-aromatic, but in the last case, the ion generated is anion, which is aromatic in nature.
Yeah. So you are correct in one way, but when you consider the product's perspective, say for example, if you take the reaction of cyclopentadienone with malononitrile and assume that the anion is first generating in the presence of base, the anion is generated on the malononitrile, right? And the malononitrile, the anion generated will add in an aldol fashion to the carbonyl because it is the electrophilic species, and then that will lead to the generation of OH. So this is the aldol product, and this can undergo condensation under the reaction condition to form this product. Okay. So this is also a pentafulvene. Okay. So assuming that the aldol reaction works to form the aldol product, which undergoes an elimination of water, dehydration, to form the pentafulvene. And if you consider the formation of this pentafulvene is flanked by two electron withdrawing groups, which will pull the electron density from the ring to the electron withdrawing group, thus making this carbon-carbon bond partially polarized in such a way that it will be CN minus plus, because of the electronegative effect of the electron withdrawing effect of the cyanide group. And this leads to the cyclopentadienyl cation, which is now anti-aromatic. Okay. So the last day we have seen the reaction of cyclopentadiene with acetone in the presence of a base. So where what happens is the base abstracts the proton and we generate the anion, and this anion adds to the acetone to form again another fulvene, where we have two methyl groups which are electron releasing in nature, and these two electron releasing groups will donate the electron density towards the ring, making the ring negative and this positive. And this leads to the aromaticity of the system. But here, this will lead to anti-aromatic system, and hence the cyclopentadienone does not react with malononitride. On the other hand, if you take propone, again under basic condition, the anion will be generated, and this adds to the propone carbonyl and the products formed. So the aldol product, aldol reaction takes place, and the condensation leads to the formation of the dicyanoFulvene, heptafulvene, where because of the presence of the strongly electron withdrawing group, again the same thing, the negative charge on the carbon attached to the cyanide group and positive charge in the ring, which will lead to the negative charge here and positive charge here, and the ring, the carbon-carbon single bond happens, and this leads to an aromatic stabilization for the 7-member ring, because it is simply like a tropylium cation, and that can have aromaticity as per the Huckel's 4n+2 rule. So this is just to remind you what we have. Various possibilities, various type of reactions, and how we can explain the concept using aromaticity and the anti-aromaticity. And also, as Jomon indicated in the beginning, don't try to buy hard things, just try to know the concept. So if you learn the concept of the ethylene, the orbitals are like one, this is the HOMO, and this is the LUMO with a nodal plane. And this knowledge is sufficient for you to begin. Okay, so this is the psi 1 and this is the psi 2 of allyl system, butadiene system, hexene, everything. And depending upon the number of atoms, say for example, we have 2 orbitals and 2 carbon atoms, we have 2 orbitals, one is the bonding and one is the anti-bonding. When we have 2, instead of 2, 3 carbon atoms, the allyl system, we have 3 orbitals related to that psi 1, psi 2, psi 3, depending upon the number of nodal planes. So here it is ethylene, so 0 nodal plane, 1 nodal plane. If it is a 3 carbon, you have 3 molecular orbitals, 0 with no nodal plane, 1 nodal plane, and 2 nodal plane. And then with that expansion of this concept to butadiene, hexatriene, and all the molecules, we can apply the same logic. And this concept is also very much important to what we are going to discuss today on pericyclic reactions. So pericyclic reactions are reactions which proceed in the presence of heating condition or photochemical condition, or photochemical condition means you expose the reaction mixture to certain radiations. So why pericyclic reactions? Because in most of the simple organic chemistry reactions, so for example, the reaction which we learned in the previous slide, it is an aldol reaction. So you have a substrate, you have an electrophile, and you have a base, the base abstracts a proton, generating a nucleophile. It adds to the electrophile and forms a new carbon-carbon bond. So typically, most of the organic reactions proceed via a polar or radical pathway. Say, for example, if you want to prepare benzyl bromide from toluene, it is a radical reaction. Or generally, all the other organic reactions proceed in a polar pathway because ionic mechanism. So it proceeds via the generation of anions, and it reacts with the electrophile, forming a new carbon-carbon or carbon heteroatom bonds. So there comes the difference between a different class of organic reactions, which is otherwise known as pericyclic reactions. The beauty of these reactions are this does not involve any polar or radical rearrangement. And most of this reaction takes place in the presence of heat or a source of light, H nu, or in other words, thermal or photochemical condition. And more importantly, there is no presence of a base or catalyst. Without base or a catalyst. And these reactions proceed via a concerted transition state. We will come to that details. A concerted transition state, which is cyclic in nature, and there is no intermediate in the reaction. So in the previous slide, we have seen an anion generated from malononitrile in the presence of a base. This anion adds to the carbonyl of cyclopentadienone, generating an initial intermediate, an alcohol. So it will first form the alkoxide via the nucleophilic addition, and the alkoxide gets protonated to form the alcohol, which eliminates a molecule of water to form the desired product. So there is a distinct mechanism where it proceeds via some intermediates. But in pericyclic reaction, there are no intermediates. And more importantly, the process of bond formation or bond breaking take place simultaneously. So it takes place at the same time without the presence of any intermediate under the reaction condition. So these are the beauty of pericyclic reactions. So these reactions proceed either, so you combine A plus B in the presence of heat or a photochemical reaction condition, or you take a molecule A, just heat it or shine light, it gives or it leads to the formation of the product. So usually, again, this is something very much known to you, the reactant, and it reacts to form the product having the lower energy, and it forms via a cyclic transition state which is of higher energy, and the cyclic transition stage will lead to the formation of the product without any intermediate. So the bond formation and the bond breaking will take place in a concerted manner with a cyclic transition state, and more importantly, no intermediate is detected in this type of reaction. So basically, the pericyclic reactions, so all the pericyclic reactions can be classified into three important categories. And I'm sure you are all aware of it. These are the electrocyclic reaction, cycloaddition reactions, and sigmatropic rearrangements. So electrocyclic reactions, cycloaddition reactions, and sigmatropic rearrangement. So in electrocyclic reaction, what happened is a conjugated system of double bond. Say, for example, we can consider butadiene or a 1,3,5 hexatriene or octatetraene or whatever. So this can undergo, if you heat it, this can undergo a 4-pi electrocyclization to form a cyclobutane. So that indicates that you generate a new sigma bond at the expense of 2 pi bonds. Or in other words, one new sigma bond is formed in an electrocyclic and in cycloaddition reaction, we have different types of cycloaddition reactions starting from 2+2 or the classical 4+2, which is otherwise known as the Diels-Aldol reaction, which is represented here, where again at the expense of pi bonds, you generate 2 sigma bonds. This leads to the formation of the cycloaddition. 4+2, 6+2, 8+2, higher order cycloaddition, or whatever. And the electrocyclic reaction, it can be 4 pi or 6 pi or 8 pi or 10 pi or whatever. So there are different types. And the sigmatropic rearrangements are the rearrangements where one sigma bond is formed at the expense of another sigma bond with a reorganization of the pi electron density. Say, for example, here, this is known as a 3-3 sigmatropic rearrangement, where what we usually do is we identify the sigma bond which is cleaving. So this is the sigma bond which is breaking. And with those 2 carbon, we number 1, 1. These are the carbons which are breaking. And then we number the atoms across the pi system. So from here, it is 1, 2, 3. Here it is 1, 2, 3. So it is a 3-3 sigmatropic rearrangement leading to the formation of a different product. And so these are the 3 typical reactions in pericyclic reaction. So where a sigma bond is broken in the sigmatropic rearrangement and a new sigma bond is formed and the number delta sigma is equal to 0. So now we go slowly to different types of reaction, the different types of electrocyclic reaction, of different types of pericyclic reaction. We'll start with an electrocyclic reactions. So electrocyclic reactions are the reactions resulting in the formation of a new sigma bond across the ends of a conjugated polyene system. So a conjugated system. So if you take a 1,3,5 hexatriene, if it is heated at a very high temperature, it forms a 6 pi electrocyclization. The 6 pi means the number of pi electrons involved. And if we say it is a cyclization of a butadiene, it will be 4 pi because it is only 2 pi bonds with the 4 pi electrons involved to form this product. So depending upon the number of pi electrons involved in the reaction, we can call it as a 4 pi, 6 pi, or whatever. So it is not only limited to ring formation, but also to the ring opening. So for example, a cyclobutene at 200 degrees Celsius, it can undergo the cleavage of this sigma bond to form a cyclobutadiene. Butadiene. So it is just a reverse of the 4 pi electrocyclization reaction. Or this type of hexatriene system can also undergo a new carbon-carbon bond via a 6 pi electrocyclization to form this compound having a 3-membered ring fused to a 6-membered ring. So these are all the electrocyclic reactions or the pericyclic reactions, such as electrocyclic reactions and the cycloaddition reactions. These are all governed by a set of rules by Woodward and Hoffmann. And I'm sure you will be knowing Woodward, who got the Nobel Prize in Chemistry in 1965 for his excellent work in the art of photosynthesis, art of organic synthesis, organic synthesis. So he got a Nobel Prize in 1965. And I'm sure you also know Hoffmann. So Hoffmann, again, he got the Nobel Prize in Chemistry in 1981 for conceptualizing this set of Woodward-Hoffmann rule. And the Nobel Prize in 81 was awarded to Hoffmann and another professor, Fukui, Kenichi Fukui from Japan. And yeah, it's too sad, but Woodward passed away in the year 1979. Otherwise, he would have also got the second Nobel Prize in 1981. Okay, so this is just a history about the Woodward and Hoffmann. And there are some set of the rules which can predict the stereochemical outcome of the pericyclic reactions, such as electrocyclic reactions and the cycloaddition reaction. So the rule says that if the first thing to identify is whether our diene or triene or tetraene under consideration is whether it is a multiple of 4 or it is 4n plus 2. So, and there are two types of ring closing possible. The two types of ring closing possible are, one is cone rotatory ring closing and the second is a disc rotatory ring closing. So we will come to that soon, what is meant by ring cone rotatory or disc rotatory. So the rule says that if you have a 4n pi system, the important or the preliminary member is butadiene. So if you have a 4n system where n is equal to 1, you have butadiene, or we can also have this octatetraene, 8 pi system. So this is 4 pi system. So where the reaction proceeds in a specific way for a heating reaction or a thermal reaction or a photochemical reaction. So for a 4n system, the cone rotatory motion, so a thermal reaction proceeds via a cone rotatory motion or cone rotatory ring closure of orbitals. And for photochemical reaction, it proceeds only via disc rotatory ring closure. So I will not go to the 4n plus 2 now. So just see what do you mean by the 4n and 4n plus 2 or 4n cone rotation and disc rotation. And I have told you we encounter this pericyclic reaction only 2 times. One is thermal reaction and the second one is photochemical reaction. So thermal reactions means we apply heating condition to the substrate. And in photochemical reaction, we apply a source of light, a UV or visible light, or in some cases IR radiation. So what happened is, under the thermal reaction, in all thermal reaction, we consider, or mostly for all the electrocyclic reaction, we consider a specific set of molecular orbital which is the highest occupied, or in other words, we have to consider, for example, in a given set of reaction, we have to consider the HOMO of the participating system. Say, for example, if you take generally butadiene, so for the time being, you forget about the substituent. If you take butadiene, we know there are 4 molecular orbitals. Out of them, 2 are bonding molecular orbitals and 2 are anti-bonding molecular orbitals. And we also know if we have to fill the electrons in Psi1, Psi2, the Psi1 2 electrons, Psi2 2 electrons. So Psi2 appears to be the HOMO of butadiene, normal butadiene. Under photochemical irradiation or upon shining light to butadiene, what can happen is one of the electron present at the higher energy level say for example, in this case, this, it will be promoted to the next orbital of psi2 to psi3. So in general, for a photochemical reaction, the HOMO of butadiene is psi3. However, for a thermal reaction, the HOMO of butadiene is psi2. So this is the HOMO of thermal reaction. Or in other words, the LUMO of thermal reaction and the HOMO of photochemical reaction are one and the same. I hope you understand. So in a photochemical reaction, one electron in the higher energy level is excited to the next level. So in butadiene, we have electrons in psi1 and psi2. So one electron from psi2, the higher energy system, is promoted to the next higher orbital, that is psi3 for butadiene. So psi3 will become the HOMO of butadiene under photochemical condition, whereas psi2 remains as the HOMO under thermal condition. And now we have to see the orbital of HOMO under thermal and photochemical state condition. So this is psi2 under thermal condition and psi3 under photochemical condition. So now the most important thing. So according to the Woodward-Hoffmann rule, we need to consider the frontier orbitals. That means the HOMO of the molecule. So for the thermal condition, the HOMO of butadiene is psi2. Okay, and now we need to identify how the participating orbitals, say like C1, C2, C3, and C4, when butadiene is cyclizing to form this cyclobutene molecule via the formation of a new sigma bond between C1 and C4, and see the orbital lobes, the C1, C2. So if you see, if I use the shaded one as positive, the positive is above, positive is below here in C4. So what is the efficient way one can combine psi1 and psi2 for a favorable overlapping? A favorable overlapping means if you have, say, 2 pi orbitals minus so this is the two type of overlapping where also 2 pi orbitals in the same phase, and if we have the 2 pi orbitals in the opposite phase, so this is the same phase, plus minus plus minus. Okay, so for an efficient overlap between these 2 pi orbital, the positive end should of this one and the positive end of this one on the right side should come closer, so that it can form a effective overlap like this. On the other hand, at the bottom, if this positive and negative, if this has to be undergoing, or this has to undergo an overlapping, positive and negative cannot overlap. Okay, that we know. So one way to do is this can come like this, and this can come like this. That means these 2 orbitals can rotate in the same direction. So here positive will come down and here this will go up so that these two positive will come together. Or in other words, we rotated the orbital lobes in the same direction, so that you get to the same system. But here, what we have done is this rotation of the orbitals were done in opposite direction, because this is done in clockwise direction, this is in anti-clockwise direction. Okay, so a clockwise rotation of the orbital lobes will lead to cone rotation, and an anti-clockwise rotation of the orbital lobes will lead to the disk rotation. So that is what we have discussed previously, the cone rotation and disk rotation. So now you take this information, cone rotation and disk rotation, and apply it to butadiene here. So here we have seen the orbital lobe positive above, negative at the bottom, and at C4 negative at the top and positive at the bottom. So assume that we need to have an effective overlap with the combination of these shaded lobes. So the way to do this is to take this, or if you take the other way around, take the negative lobe. So this arrow is clearly right representing it. So if you rotate it in the anti-clockwise direction, this shaded lobe will move above, and here also if it rotated in the anti-clockwise direction, this shaded minus lobe will come down. So when we rotate the two lobes in the clockwise direction, this is a cone rotation, and this leads to a new carbon-carbon bond. However, if you think about a disk rotation here in this structure, a disk rotation cannot lead to an effective overlap. Say, for example, disk rotation means we rotate one in the anti-clockwise direction and one in the clockwise direction, so the reverse direction. So then the similar lobe cannot come closer. So this, in other words, the cone rotation leads to the formation of the cyclobutene, and with this rotation of the lobes, we are rotating both the lobes in the clockwise direction. So this substituent attached, so methyl will go up and this methyl will come down. So those two methyl groups are far away, which leads to the formation of the trans isomer. I hope it is clear. So this is otherwise known as the cone rotation. So the cone rotation always takes place when the two participating orbitals, the lobes are opposite sign, so that the same rotation or the rotation at the same direction will allow the lobes to come closer and overlap. So cone rotation takes place when the lobes are with opposite sign. Okay, so you have, I hope you understand. So here it is the shaded one above, here it is a shaded one down. So these are opposite direction. So for the effective overlap between the two orbitals, one has to rotate, or both of these orbitals have to be rotated in a same direction, either in the clockwise or the anti-clockwise direction. So this leads to the thermal cone rotation. That means a thermal 4-pi cyclization is cone rotatory under thermal conditions, and this is allowed. However, the 4-pi disrotation thermal disallowed. Why? A disrotation means these two lobes have to go in the opposite direction like this. and there is no possibility of such overlap. And now we come to the photochemical excitation, where earlier we considered the Psi2 of butadiene, and now we have to consider the Psi3 of butadiene because the Psi3 of butadiene, because one of the electron is excited to the Psi3 level. So Psi3 is the HOMO for butadiene under photochemical condition. So Psi3. So you can see Psi1 and Psi4, the lobes are on the same side, and for Psi2, the lobes are on opposite sides. So we know for closing it, the rotation has to be in the same direction. And now Psi3 case, the photochemical one, where one electron from Psi2 is excited to the higher energy Psi3. And suppose we try to close these two carbons, the only possibility is, say for example, this one, we can move in this anti-clockwise direction, or this lobe again in the clockwise direction, so that two lobes are rotated in the opposite direction, so that these two will come closer and overlap. And in that process, what will happen is, so earlier the two methyl groups were far away, and when we rotate it, say in the anti-clockwise direction, this methyl will come down, and this is rotated in the clockwise direction, this methyl will come down, so that the two methyl groups will come closer, or it leads to a cis isomer. So a photochemical reaction, 4-pi disrotation photochemical allowed, whereas a 4-pi dis or cone rotation photochemical forbidden or disallowed, forbidden. So the rule is 4-pi system, cone rotation thermal allowed, photochemically forbidden. 4-pi system, disrotation photochemical, it is allowed, thermal it is not allowed or forbidden. So this is the one of the most important rule, the Woodward-Hoffmann rule for electrocyclic reactions. And with the knowledge of this electrocyclic reaction, say for example, here we have a butadiene having 2 substitution, and 2 substitution means we know that if you look at the orientation of the double bond, so this double bond is a trans-oriented double bond, or is a E olefin, and this is also an E olefin. And when we do a thermal reaction, so the thermal reaction according to the Woodward-Hoffmann rule, it is a cone rotation. Cone rotation means one has to be clockwise and one has to be, sorry, both has to be in the clockwise direction, so that this leads to the formation of the trans isomer. And in the case of the photochemical condition, it leads to the cis isomer. So remember, the photochemical reaction, the thermal reaction, the 4-pi electrocyclization reaction, cone rotation, 4-pi is thermally allowed, and the photochemical reaction is thermally not allowed, or the cone rotation, under cone rotation it is not allowed. And photochemical reaction, 4-pi, it is disrotatory, which is photochemically allowed, whereas the cone rotatory mode, the photochemical is forbidden. So it forbidden means if you take the Psi3 of butadiene, you cannot close it. So that means if you do not, even if you do not know the Woodward-Hoffmann rule, by constructing the side 2 or drawing the side 2 and side 3 of butadiene, you know sort of whether you can form the molecule or not with the idea of the con rotation and disrotation. So with the knowledge of con rotation, we can easily say that the thermal reaction is con-rotatory and photochemical reaction is disrotatory in 4-pi system. And just like what we have learned in aromaticity, this concept we can also apply to any 4n-pi systems. So you can extend the 4-pi electrocyclic reaction to an 8-pi system, 12-pi system, or any 4n-pi system. And the rule is 4n-pi con-rotation or the thermal condition, it only proceeds via a con-rotatory motion. So this is what we have seen. So if it is a con-rotatory mode of ring closure, the con rotation, it leads to the formation of the trans isomer, and the disrotation leads to the formation of the cis isomer. So please remember, this is the way usually in competitive exams they ask. They give the question of a butadiene with a specific geometry of the participating atoms or grooves attached to the 1,4-diene. And then in the thermal condition, what will be the product, and photochemical condition, what will be the product. This will be usually asked in GATE and CSIR exam. So the idea is you just need to know the butadiene molecular orbitals, the psi1, psi2, psi3, and identify under thermal condition which will be the HOMO and photochemical condition which will be the HOMO. So if it is the thermal condition, the psi2 is the HOMO, and depending upon the grooves attached, so the rotation will take place in the same direction in con rotation, and for this particular orientation, the same direction rotation of these grooves will lead to the formation of the cis isomer, and which photochemical, the opposite direction leads to the trans isomer. So with the simple knowledge of the psi1, psi2, psi3 and psi4 of butadiene, and you know psi2 is HOMO for heating condition and psi3 is HOMO for photochemical reaction. And whenever you have, even if you don't by heart this, you just need to know the molecular orbitals of butadiene. With the problem, you can see the only difference is, say here, this olefin is E-olefin or trans, but this olefin is, say you can see it is a cisoid one, so it is an Z geometry. So with the rotation, as I told you, the con rotation or disrotation, whether it is going in the same direction or in the opposite direction, the stereochemical outcome can be defined based on the Woodward-Hoffmann rule with an idea about which is psi2 and which is psi3 in the molecule. So the key to success for identifying all the electrocyclic reaction is, the first thing to do is identify the molecular orbitals of the system. So if, for example, 4-pi system, the molecular orbitals of 4-pi system, the simple example is butadiene. So we know psi1, psi2, psi3 and psi4, and then identify which is HOMO, which is LUMO. And suppose it is an 8-pi system, like a 1, 3, 5, 7 octatetraene. So then we have 8 molecular orbitals, then psi4 will be the HOMO. So the concept will be the same. So the extreme end, the terminal carbons, the lobes will be in such a way that only con rotation leads to a thermal cyclization and disrotation leads to a photochemical cyclization reaction. So this reaction is again, if you know the ring formation or the electrocyclic reaction, sometimes in questions they ask you, like if you have a butadiene with a butene, cyclobutene, when this is heated. So the same rule is applicable in the opposite direction for ring opening reactions. So if you have a ring opening reaction, say like earlier we were now discussing about the ring closing, so it is also applicable to ring opening reaction. So what happens in ring opening reaction is the concept is reversed. So the rule is the cone rotation. Now the thermal 4-pi system, it is not allowed for ring opening reaction. The photochemical reaction is allowed. So the rule will be opposite, but what I suggest you is you just remember, if it is a ring opening from the cyclic compound, assume the possible product form, the ring open form, and apply the rule what we have learned, which will lead to the product. So that is the best way for doing this ring opening reaction, because if you know the ring closing reaction, ring opening reaction will be rather easier. The concept is, the rule is just opposite. You don't have to by heart, but what I suggest is all of you, for the ring opening reaction, you think in the reverse direction and imagine at the product. The only difference will be the stereochemical outcome. And if you are asked a cyclobutene opening, you will come up with either this product or this product, one of these, and see either this or this under the reaction condition will lead to the product. So that is the best way to identify the product in a ring opening reaction. So the rule is, again, if you try it in a piece of paper, you can understand that the rule will be just the opposite. So if a ring closing reaction is cone rotation or ring formation reaction, a cone rotation is a thermally allowed, but for the ring opening reaction, the thermal, it is disrotatory. So the cone rotatory ring closing will be the same as disrotatory ring opening. Okay, so far we have seen the 4-pi system, 4-pi system where we have the cone rotation and disrotation, and we have seen that the cone rotation leads to the thermal 4-pi cyclization of all the 4-pi electrocyclization. Cone rotation leads to the product. The disrotation is forbidden. On the other hand, the photochemical condition, the cone rotation is forbidden and disrotation is allowed. So now you take the same concept for a 4n+2 system. So 4n system we know with a simple butadiene. So 4n+2, the best example is (135) hexatriene. 135 hexatriene, and it is having 6 molecular orbitals, and as you can see, it has 6 molecular orbitals and 6 pi electrons. So which one will be the Psi3 or the HOMO of this system? So Psi3 will be the HOMO, and the Psi3 means it is the one having 2 nodal planes. Okay, 2 nodal planes. So what I will do is plus minus minus minus, minus, plus, plus, and now this is plus. So this is the HOMO Psi3 of the hexatriene, 135 hexatriene. I'm not writing all from Psi1 to Psi6 because I hope you remember all these things. And if we are asked the because Psi4 is the HOMO for the photochemical reaction, right? So Psi4 means you have 3 nodal plane, 1, 2, 3. So here, if I start with plus minus, here there is a nodal plane, minus, minus, plus, plus, and then another nodal plane, plus, plus, minus, minus, and again a nodal plane, minus, plus. So this is Psi4, and Psi4 is the HOMO for photochemical reaction, and Psi3 is the HOMO for thermal reaction for a 6 pi system, and 6 pi will fall under the category 4n plus 2. Okay. And if we want to cyclize this hexatriene at the C1 and C6 position, where the lobes, both the lobes are on the same side. So what you have to do, this lobe has to be rotated in this clockwise direction. This lobe has to be rotated in the anti-clockwise direction so that both the positive will come closer. That means this is disrotatory motion, right? You are rotating the lobes in the opposite direction. So the 4n plus 2 pi system, the thermal reaction is disrotatory, whereas in the 4n system, the thermal reaction was conrotatory. That just a few minutes ago we saw. So with this knowledge of the molecular orbital, so Psi3, so again I'm saying I'm not writing all the molecular orbitals of hexatriene because I'm sure you know how to draw it from Psi1, Psi2, Psi3, Psi4, Psi5, Psi6, where you have 0 nodal plane, 1, 2, 3, 4, 5 nodal planes. And since you have 6 pi electrons, we fill like this. So Psi1, Psi2, Psi3. Psi3 is the HOMO for thermal reactions. And now for closing these two orbitals, we know the lobes are on the same side. So we have to rotate it in the opposite direction so that the positive signs will come together. So why we are rotating it in the clockwise or opposite direction? Why not the same direction? Say suppose you rotate this in the clockwise direction, so the positive lobe will come like this, and again this also in the clockwise direction, so that positive will come down, the negative will come out above. You understand? So the clockwise direction, the positive will come to the horizontal direction. And this also in clockwise means negative come to the horizontal direction and the positive and negative will come, so that will not give to an effective overlap. For effective overlap, if we move the positive lobe here on clockwise direction and this one on opposite direction, anti-clockwise direction, both the positive will come together and it can overlap, and this is known as the disrotation. So for 6 pi electrocyclization, the thermal reaction proceeds via the disrotatory motion. Okay, disrotation leads to the product in the end. So the disrotation leads to the cyclohexadiene. And suppose we have two methyl groups at the end. So what will happen? So these lobes are rotated in the opposite direction so that these methyl groups also will come closer, or this leads to the cis isomer. Okay, how? This will rotate in this direction, so this will also rotate in this direction, so the methyl groups will not go far away, or it will come closer. And now see the photochemical reaction, the 4n+2 system. And remember, in the 4n+2 system, or the 6 pi to be specific, the electrocyclic reaction under photochemical condition, what will happen? One of the electron in Psi3 gets excited to Psi4. This is the nodal plane, don't get confused. It is Psi1, Psi2, Psi3, Psi4, Psi5, and Psi6. So now the electrons get excited to Psi4, and Psi4 is the HOMO. And we have written the Psi4. And see how we can combine C1 and C6. And here the lobes are on opposite direction. So if you want this positive to come closer, we rotate it to in clockwise direction, and this positive charge can come closer by rotation in the clockwise direction. So that is, it is a cone rotatory motion. So the cone rotatory motion, so this is clockwise direction, this one also clockwise direction, or both the lobes are rotated in the same direction, which leads to the clockwise rotation or the cone rotation. And if you see, we have a substituent here, methyl group, and we can see that if you rotate it, the clockwise rotation of this lobe will make this methyl go this direction, and this direction the methyl group will come down, so the two groups will go far away, or as a result of this clockwise the same direction rotation, this leads to the formation of the trans isomer under photochemical reactions. So the cis isomer will be formed under thermal condition, and the trans isomer will be formed under photochemical condition. So the reason is, or this is governed by the set of rules which is known as the Woodward-Hoffmann rule. But even without the knowledge of the Woodward-Hoffmann rule, we can conclude both the results. Say, for example, in the 4n system, so like these two lobes, for combination of these two lobes, these lobes are rotated in the same direction, because this has to come down, this has to go above. So this is the same direction, so that it is cone rotation leading to the trans isomer in the case of a 4 pi system, whereas it leads to a disrotation in the case of a 4n+2 or 6 pi electrocyclization system. And remember, this knowledge of this cone rotation, say for example, the simple ring closing reaction, 6 pi electrocyclization, cone rotation, photochemically allowed, thermally forbidden. And just now we have seen the 6 pi cyclization, or in general 4 pi electrocyclization, the disrotation is thermally allowed, photochemically not allowed. So this is the rule, Woodward-Hoffmann rule. But with the knowledge of the molecular orbitals, even without by hearting these rules, we can understand the stereochemical outcome of an electrocyclic reaction with the knowledge above of this orbital symmetry. I hope it is clear to you. And with this, we can also extend, or with this concept can be applied to various organic transformations. For one of this example is written here, this benzocyclobutane. This can undergo a ring opening, a retro 2+2, or the ring opening 2+2, 4-pi cyclization. So not 2+2, a retro 4-pi cyclization, and this leads to the formation of the butadiene, just like a cyclobutene opening to butadiene. So this is what is happening, and then this leads to the formation of an olefin or a butadiene system, and this can cyclize to a 6-membered ring, like a Diels-Aldol reaction, which will be the next topic. Diels-Aldol reaction. Okay, so this is one of the important application of this type of pericyclic reaction. One can have this reaction happen under either thermal condition or photochemical condition without the presence of any reagent, any catalyst, no other extra reagent, where this reaction proceeds via a cyclic transition stage and leads to the formation of the product. So with this, we will move to the cycloaddition reactions. So cycloaddition reaction, as I told you, it can start again from simple olefin. So just a electrocyclic reaction, we start from butadiene, because that is the first member we can form a cyclic system with at least 4 participating atoms, because 2 pi bonds are required for the closing. And cycloaddition reaction, we can start from the 2+2 cycloaddition reaction, 2+2 cycloaddition reaction. So here again, you need to know the concept of these molecular orbitals. So what will happen in this reaction is, say for example, if you take the molecular orbitals of ethylene. So this is the psi1 of ethylene, this is psi2. So this is the molecular orbital, this is the antibonding molecular orbital, and this is the ground state configuration of ethylene, a simple alkene. And when you shine light or apply a source of radiation, one of the electron gets excited to the higher energy level. So the electron gets excited from, or the electron move from psi1 to psi2. This is the psi2 of ethylene. So according to the Woodward Hoffmann rule, in all the cycloaddition reaction, the HOMO of one of the component. So in the electrocyclic reaction, say for example, we are getting butadiene converting to cyclobutene, or the ring opening of cyclobutene, we have only one component, right? So there is a single component involved. You take your olefin, heat it, and get the cyclized compound, or take the cyclic compound, heat it, it undergo ring cleavage to form the open compound. But also we have seen in this case, to define or to know the stereochemical outcome of the reaction, we need to know the HOMO of the participating system, or which is the HOMO of the molecule, or which is the HOMO under thermal condition or the photochemical condition. And we know the photochemical condition is where the high energy electron gets excited to the next higher level. So in 2+2 cycloaddition reaction, or all the cycloaddition reaction, obviously we have 2 components, and the rule is that here HOMO of one of the reactant overlap with the LUMO of the other component. So in 2+2 cycloaddition reaction, we have only 2 molecules of ethylene, because this is 2 pi, this is also 2 pi, and this combines. So if you consider a simple 2+2 cycloaddition reaction where you think about the combination of 2 molecules of ethylene, it forms a cyclobutane, right? So it forms like here, this is a cycloaddition reaction, and 2+2 cycloaddition reaction. Or if you think about the Diels alder, it is like this, a 4+2. Okay. So here what happens is we need to consider the overlap of the HOMO of one species and the LUMO of the other species. So HOMO of one of the participating system. Say for example, if you take the HOMO of one molecule of ethylene. So one molecule of ethylene. So I'm writing ethylene like a double bond. So this is the HOMO of ethylene. And LUMO of the second molecule of ethylene. That means this is the LUMO. And that also I write. And here what you have to see is when you write this HOMO and LUMO, whether the orbitals are, say like you take ethylene, one molecule of ethylene, second molecule of ethylene, and this is the HOMO of first molecule of ethylene, this is the LUMO of the when we try to overlap the HOMO with LUMO, if you see the right side lobes, these are perfectly overlapping because these are on the same side. But on the left side, positive and negative, so the effective overlapping is not happening. So this is one mode of overlap. Okay, and now take the 2+2 photochemical reaction. So if you take 2+2 photochemical reaction, what will happen is the electron in the HOMO of one of the ethylene get excited to the higher level. That means this HOMO, one electron gets excited to the higher level. That means you have to consider the LUMO of the first ethylene, that is the HOMO, or a HOMO of the first ethylene, and then the LUMO of the second ethylene remains the same. Because in photochemical reaction, the HOMO of one ethylene changes to the next level, and the LUMO remains the same because LUMO is always the same. Okay. Lowest occupied molecular orbital of the second participating atom. And now here you see, if you have the HOMO of the first ethylene molecule after excitation, okay, and this LUMO of the next molecule which is not excited. So this is the side 2 is the LUMO. And if you try to overlap the two orbitals, this is both are perfectly matching. So this type of hello.
Yes.
Hello. Can you hear me?
Yes, yes.
Joma?
Yes, yes.
It's audible. There was a disturbance in between.
Okay. Okay. Thank you. So this type of overlap where both the lobes can be perfectly overlapped in phase, this is known as the suprafacial overlap. Suprafacial means in both cases it is perfectly overlapping. But in the previous case, we have seen this is perfect but the second side, one lobe is positive. These are shaded one, but here it is not the shaded one. So this side is not perfect. So this is known as interartificial overlap, which is not effective. So here, this one side is fine, the other side is not fine. So this is not an effective overlap, but on the other hand, this one will be an effective overlap, a superficial overlap. So what I have told you in the last 5-10 minutes is 2+2 cycloaddition reaction, which happens thermally, is in one side it is possible, but the other side is not possible, or it is interartificial. That means it is not possible to form the molecule, or it is thermally forbidden. On the other hand, the photochemical version, where one molecule of or one electron gets excited to the higher level, the Lumo, where the effective overlap, the superficial overlap takes place, this is allowed. So in 2+2 cycloaddition reaction, thermally it is not allowed. So 2+2 cycloaddition reaction thermal is forbidden, whereas 2+2 cycloaddition reaction photochemical is symmetry allowed. So this is the Woodward Hoffmann rule for 2+2 cycloaddition reaction. And now you take this information to 4+2 cycloaddition reaction. So the 2+2 cycloaddition reaction, the product formation can also be invoked via the radical mechanism. You homolytically cleave this pi bond to form two radicals, and then this radical coupling can take place to the formation of the same product in the same way what we envisioned in a photochemical reaction, but only the photochemical reaction, the 2+2 cycloaddition works. The thermal reaction is forbidden. Okay, so more important thing is, in the case of photochemical reaction, the 2+2 cycloaddition reaction, as I told you, in only it proceeds via photochemical condition or in the presence of irradiation. So the 2+2 cycloaddition reaction, so if you have this olefin reacting with the cyclohexenone, you get a 2+2 cycloadduct like this, and this 2+2 adduct formed will be highly regioselective. What do you mean by regioselective? So one can also form this product also, right? So where the olefin, the methyl groups are above and the CH2s are down, and the 2+2 cycloaddition can lead to this product as well. But this product is not formed because of the presence of this carbonyl group. This methyl group always prefers at the opposite side, and this leads to the regioselective formation of this product. And we have seen that thermal 2+2 cycloaddition forbidden, right? And photochemical 2+2 allowed, because it proceeds via superficial overlap, but this one is interartificial. But there is an exception. Whenever we have a olefin which is part of a system like this, where you have a carbonyl and an olefin which is known as ketene. So the ketene can undergo a 2+2 cycloaddition under thermal condition. So this is something which is contrary to Woodward-Hoffmann rule. We know that 2+2 cycloaddition reaction is thermally forbidden. The only exception is the ketene and ketamine type of system. These reactions are allowed under heating condition. This is because if you look at the ketene structure, the middle carbon atom is sp hybridized and the terminal 2 carbon atoms are sp2 hybridized. So these two participating pi bonds in ketene, these two are perpendicular to each other or at right angles to each other. And these orbitals can overlap with the orbital of olefin in an supramolecular fashion, not the interofficial. And because of that, only alene or ketene system, this undergo 2+2 cycloaddition reaction. And how we can get a ketene? So the ketenes are generated from the corresponding acid chloride having an alpha CH bond, alpha CH containing acid chloride. When you treat with a mild base, the base abstracts this proton and then eliminates the chloride to form the ketene having a carbon also here, and the ketene can undergo a 2+2 cycloaddition reaction. So these are the typical cycloaddition reactions. So the 2+2, 4+2, 4+4. So this we have seen the 2+2 cycloaddition, which is thermally forbidden, and we know the reason, and photochemically allowed. And then 4+2, 4+4, and wide variety of systems. And now we come to the most important reaction. So the Diels-Alder reaction, which is otherwise known as the 4+2 cycloaddition reaction. So the 4+2 cycloaddition reaction is the Diels-Alder reaction. So we have seen a 2+2 cycloaddition reaction just now, and we know that 2+2 cycloaddition reaction, thermal condition is symmetry forbidden. It will not happen, and photochemical reaction, it happens asymmetry allowed. Sorry. So Diels-Alder reaction is thermal cycloaddition between cis-oid conjugated diene and a dienophile. So a diene reacting with a dienophile to form a 6-membered ring. A 6-membered ring is formed a concerted 4+2 addition, highly regioselective. And in the case of 2+2, we know it reacts to form a 4-membered ring, a cyclobutene 2+2, and this is thermally not allowed and photochemically allowed. And here, this is a heating reaction, a thermal reaction condition for the development. Professor Diels and Kurt Aldol received the Nobel Prize in Chemistry in 1950. So what happened in Diels-Alder reaction? So the same thing. So what we can do is we have the 4+2 cycloaddition reaction. 4+2 cycloaddition reaction means you have a diene and a dienophile. Okay, and as per the concept of cycloaddition reaction, in all the cycloaddition reaction, what happens? Essentially, the HOMO of one component overlap with the LUMO of the other component. Okay. So assume if you take the HOMO of ethylene, this is the HOMO of ethylene, the psi1. Okay, so that both two lobes are on the same side. And LUMO of butadiene, LUMO of butadiene means psi3 of butadiene, where you have one nodal plane here, second nodal plane here. Okay, and psi2 having one nodal plane. And if you have this psi1 of ethylene, that is the HOMO of ethylene, LUMO of butadiene, it overlaps. It overlaps. Look, this side it can overlap, this side also it can overlap. Or it means it is a constructive overlap or a superficial overlap. It does not have to be the HOMO of ethylene and the LUMO of butadiene. It can be other way around. Say, for example, instead of the HOMO of ethylene, if we are taking the LUMO of ethylene. So LUMO of ethylene means opposite charge, right? And now, if we take LUMO of ethylene, then HOMO of butadiene has to be considered. HOMO of butadiene means Psi2 with a single nodal plane. And here also the overlap is efficient. That means it is suprafficial. So we have seen previously the 2+2 cycloaddition reactions. Here the 2+2 cycloaddition reaction under heating condition, this is suprafficial and this is symmetry forbidden. And only photochemical reaction was allowed for a 2+2 cycloaddition reaction. And see here, this is a thermal reaction. We did not excite the electron to the higher level. So a thermal reaction, a 4+2 cycloaddition reaction is symmetry allowed, suprafficial in nature, and the reaction was, and hence it is symmetry allowed. Now imagine the photochemical reaction, a 4+2 photochemical reaction. We can take the LUMO of ethylene. So what is the LUMO of ethylene? This is the HOMO and this is the LUMO. Okay. And the LUMO of ethylene means this is the HOMO, this is the LUMO of ethylene. So the LUMO of ethylene is written. And now the HOMO of butadiene under thermal condition. So what will be the LUMO of butadiene under thermal condition? Which will be, hello? So we considered the LUMO of ethylene and HOMO of butadiene. So this is the HOMO of butadiene, that is Psi2, the highest occupied molecular orbital, and LUMO of ethylene, this is the unoccupied molecular orbital, or even if we excite one electron, or if we irradiate the butadiene, or LUMO of butadiene will be becoming Psi3, and this is having the two nodal planes. So this is not the nodal plane. So these two are the nodal plane, or Psi3 is the HOMO of butadiene after irradiation. I hope you understand. The normal butadiene, Psi2 is the HOMO, but when you irradiate, one electron will go to Psi3. So the Psi3 under photochemical condition, the HOMO of butadiene and LUMO of ethylene. And now this will overlap. Again, as you can see, the lobe on one side can be effectively overlap. The second side, this is the unshaded one, this is the shaded one. So this is not effective, or this is under-official overlap. So this overlap is not very efficient. Or in other words, the 4+2 cycloaddition reaction is photochemically forbidden, whereas the 2+2 cycloaddition reaction is photochemically allowed. I hope you were able to follow it. So remember, in cycloaddition reaction, what we have to consider is, we start with the orbital picture, the HOMO of diene and LUMO of dienophile in Diels reaction. Or in other words, the HOMO of dienophile and the LUMO of diene, both are giving the same results. Here also the same thing. If you take the HOMO of ethylene after irradiation and Lumo of Butadiene, the same thing will happen. You can also try at home when after the class. It also leads to the interfacial. So we considered the both possibilities of homo-lumo of olefin and dienophile in thermal case, which we found that thermally it is allowed, and the photochemical reaction is symmetry forbidden. And this, in majority of the cases, the Diels-Alder reaction, like most of the pericyclic reaction, these are all stereoselective. So stereoselective in the way, say like if you have an olefin which is like this, whereas both the carbon double bonds are trans, the symmetry or the stereochemistry will be preserved at the end of the cycloaddition reaction. So it is projecting above, it is projecting above. And this is true for all the Diels-Alder reactions. So since this is trans facing opposite, this is again facing trans, and this is the cis-oid, the one answer is also the stereochemistry will be different. So this is just an example of the dienophile. Here we have seen the diene, the stereochemical aspect of the Diels-Alder reaction with respect to the diene, and with respect to the dienophile also this is same. So in the Diels-Alder reaction, so if you have a cis dienophile, the dienophile, the product also it will be at the same, and the trans one, the final product, it will be at the opposite direction. And one important thing about Diels-Alder reaction is the Aldol's Endo rule. So in most of the Diels-Alder reaction, if there is a possibility of a secondary overlap between orbitals, that type of product predominates, and that is known as the Aldol's Endo rule, where the stereochemistry or stereochemical outcome of a Diels-Alder reaction is governed by the Endo rule, because the two products formed can be either endo or exo, where the exo, I will tell you the details. So if you look at this Diels-Alder reaction of cyclopentadiene reacting with another molecule of cyclopentadiene. Okay, so if you see otherwise a Diels-Alder reaction of cyclopentadiene reacting with a maleic anhydride. So this product formed is endo product. Why? Because if you think about the Diels-Alder reaction in general, so if you have a diene and we have a dienophile which is like this, okay, and the diene and the dienophile react in a suprafacial manner to form the cycloaddition reaction. And if your dienophile or diene having groups, say in this case the dienophile has an additional group which can overlap with the non-participating overlap of the diene or non-participating orbitals of the diene, this overlap leads to the formation of the endo product, where this carbonyl can overlap with this p orbital. The endo or the exo product will be above the plane of the molecule. So this is the exo product, where the maleic anhydride will be projecting away, and this is the endo product where this carbonyl can overlap with the carbon-carbon double bond via a secondary orbital interaction. And this is also possible in this particular example, the cyclopentadiene reaction with maleic anhydride. So you can see that this is the maleic anhydride overlap with the cyclopentadiene via the suprafacial overlap, to form the carbon-carbon single bond, but the carbonyl groups, these carbonyl groups, that carbon can overlap with the non-participating pi orbitals of butadiene or cyclopentadiene specifically in this case, to selectively form the endo product as a result of Diels-Alder reaction. So the secondary orbital interaction between the dienophiles and the diene, the non-participating orbitals of the diene, could result in the formation of specifically or endo product in the case. And this is also the regioselectivity in Diels-Alder reaction is either ortho or para-selective. This is depending upon the groups attached. This can vary, so the minor amount of meta products can also form, but in general, ortho or para products are predominantly formed. These are some of the examples of Diels-Alder reaction, so probably it is not very important. So again, the dienophile react with a diene to form a Diels-Alder reaction, and this reaction is very much useful for the synthesis of various products such as cholesterol and other natural products. Another important thing is the retro-Diels-Alder reaction. So just like Diels-Alder reaction is important, there is also retro-Diels-Alder reaction. Retro-Diels-Alder reaction is the reverse of Diels-Alder reaction. Say for example, if you take cyclopentadiene, so this product, cyclopentadiene, is not a commercially available molecule because at around 30 degrees Celsius, the cyclopentadiene undergoes Diels-Alder reaction with itself. To form this molecule, or this is known as dicyclopentadiene, DCP, dicyclopentadiene. So you cannot buy cyclopentadiene from any commercial source because by the time you get it, it will dimerize. So what people do in laboratory to prepare cyclopentadiene is, this dicyclopentadiene is very much cheap and commercially available, and dicyclopentadiene is the dimer of cyclopentadiene. Okay. So if you take the dicyclopentadiene and heat it around 170 degrees Celsius, what will happen is a retro-Diels-Alder reaction will happen. So a retro 4+2 will take place, and this will convert into 2 molecules of cyclopentadiene. So what people normally do is, you take cyclopentadiene or dicyclopentadiene in a round bottom flask and then fix a condenser, and here you have a receiver RB. Okay, and here the condenser is cooled by water, and now heat it at 170 degrees Celsius. At 170 degrees Celsius, the dicyclopentadiene breaks, and then once it breaks, it will be very low volatile. It will, boiling point is very less, so it will try to escape and it will go above, and from at this condenser point it will cool down and it gets condensed and it will be collected here. But one important thing to note is, if you collect the cyclopentadiene here, the collected cyclopentadiene can immediately undergo Diels-Alder reaction back to dicyclopentadiene. So what one has to do is, the collecting receiver flask has to be kept in ice well below 30 degrees Celsius. Why? To prevent the Diels-Alder reaction to form the dicyclopentadiene. Okay, so this is how people use or prepare cyclopentadiene in laboratory, by the cracking of dicyclopentadiene. Why? Because the cyclopentadiene undergoes retro-Diels-Alder reaction. So just go to how we'll see one reaction. So if we have, say for example, furan, and treat it with dimethyl acetylene dicarboxylate, what will happen? So remember, this is a very frequently used question in CSIR exams. So what will be the product of this reaction? So the reaction is again a Diels-Alder. So because this is a furan and a dienophile, a 4+2 cycloaddition reaction. And what will happen? This is the cycloadduct formed. And now here the oxygen at the ring junction or the bridgehead. And now this reaction does not stop here. What will happen? This undergo a retro-Diels-Alder reaction. How? This undergoes a retro-Diels-Alder reaction. By breaking these two carbon-carbon bonds. And now when you write the product, you will understand why this reaction happens. So these two carbon-carbon bonds are broken, and a carbon, carbon, and a third bond. So what will be formed? Acetylene. And acetylene is a gas. And what will be the product? A 3,4 disubstituted furan. So remember, this is a very frequently asked question, not only in all qualifying exams as well as our own PhD interviews. We ask students how to prepare 3,4 dicarbomethoxy furan from furan. How you convert furan to 3,4 disubstituted furan. So when you see this problem like this, a furan converting to 2 ester, you always think about introduction of furan at 3,4 position with some ester moiety. You never think about a cycloaddition reaction. So it is a very simple reaction, and the driving force is the evaporation of the generated acetylene. So furan, Diels-Alder reaction, and a retro-Diels-Alder reaction to form the 3,4 disubstituted furan derivative. Okay, so we have seen that the furan or any type of cycloaddition reaction, for example, the Diels-Alder reaction, which proceeds via the overlap between the HOMO of the diene and the LUMO of the dienophile. And for a typical Diels-Alder reaction, the rate of the reaction of a Diels-Alder reaction can be enhanced by the electron richness of the diene and the electron deficiency of the dienophile. So the diene should be electron rich and the dienophile should be electron deficient for a Diels-Aldol reaction. So if you do a typical Diels-Aldol reaction, a diene reacting with an aldehyde, alpha beta unsaturated aldehyde, the reaction works with toluene as a solvent 120 degrees Celsius. We get the 2 regioisomeric mixture because it can add like this with the aldehyde down, or you can write the aldehyde like this. Both products are possible. So if we use a Lewis acid catalyst, what the Lewis acid catalyst will do, say if you have the ester, so the Lewis acid will activate the carbonyl ester, making this carbon-carbon double bond more electron deficient. Okay. So the carbon-carbon double bond will be more electron deficient. So according to the electron deficiency or typical Diels-Aldol reaction, with the Lewis acid, the reaction rate will be enhanced. So at 120 degrees Celsius, the reaction gives this product with very poor selectivity, but with 25 degrees Celsius in benzene, in the presence of stannous chloride or stannic chloride, the reaction is highly stereoselective. So the reaction works fine, the rate of the reaction is fine, and the selectivity of the reaction is also fine in the presence of a Lewis acid catalyst. And another important thing is the Diels-Aldol reaction. One can do the Diels-Aldol reaction in enantiomerically pure form. If you use a chiral Lewis acid catalyst, one can do the Diels-Aldol reaction in chiral fashion for the construction of the 6-membered adduct with high enantio selectivity. So in the next 10 minutes, I will try to cover the sigmatropic rearrangement reactions. So the molecular sigmatropic rearrangement. So far we have seen the electrocyclic reaction, the cycloaddition reaction. So following the Woodward Hoffmann rules, the selection rules. So please remember the rule. If you don't by heart the rule, the only thing which require is the knowledge about the molecular orbitals, the psi1, psi2, psi3, psi4 of butadiene. If you know that, you can develop everything and then give an interpretation of all the Woodward Hoffmann rules. You don't have to by heart anything. And that application you can use for a 4-pi electrocyclic reaction. The quantitatory motion, reaction is thermal, and disrotation is allowed under photochemical reaction. And the same thing, you can extend these two photochemical, the 4n+2 rules. And in a different context, we also explained the cycloaddition reaction, the 4-pi cycloaddition reaction. We found it is thermally forbidden and photochemically allowed. And what you have to know is, under photochemical condition, one electron of the diene or the dienophile will be pushed to the next orbital, so that HOMO and LUMO will change, so that the HOMO of one participating component and the LUMO of the second component will overlap, leading to the formation of a cyclic compound. So in sigmatropic rearrangement, what usually happens is breaking of a sigma bond and formation of a sigma bond via migration through the pi electron system. And that leads to the formation of a new pi bond, reorganization of the pi system. And the rearrangements are different types. You can have 1,3 sigmatropic rearrangement, 3,3 sigmatropic rearrangement, and the numbering I have just shown you, and we can discuss a little bit more. So this is a typical 1,3 sigmatropic rearrangement. So what we do is we give the numbering to the sigma bond which will break. Here it is. This is the bond breaking, and 1, 1, and then the other portion 1, 2, 3. So if you have a system like this, and now if you are breaking this sigma bond, you number the 2 carbons as 1, 1, and then extend the numbering to the end of the pi system, 2, 3, and then draw the arrow to form the product, and this is a 3,3 sigmatropic rearrangement. You form a new sigma bond with breaking of a sigma bond with the reorganization of the pi cloud. So these are some of the typical 3,3 sigmatropic rearrangements, and one of the important 3,3 sigmatropic rearrangement is the Claisen type rearrangement. The Claisen type rearrangement or the Kopp rearrangement. So typically we can represent it as, so if X is equal to oxygen, it is a Claisen rearrangement, and if X is equal to CH2, this is a Kopp rearrangement. So for example, the one we have seen, so what happens? So since we are discussing with Kopp rearrangement, I hope all of you will get this answer. But how you answer this question? So we need to cleave a carbon-carbon bond, and we need to introduce a 4-carbon tether, right? So that means we need to introduce 4-carbon tether, and this has to be broken. So assume that we have something like this, and this is our bond, 1, 2, 3, 4, 5, 6, and this is our substrate class. And if we have this type of thing, then we can undergo, or we can do a 3,3 sigmatropic rearrangement cleaving this bond. So what we have to do is we have to introduce 2 vinyl groups or vinyl groups. Okay, how we can do it? So first to do is, one, we can always do just like what we have seen, the vinyl Grignard reagent. But other one, how we will do? Say for example, here we have an alpha ester functionalized ketone. So if we have a vinyl sulfone SO2pH and a base, so what the base will do? The base will abstract this acidic proton, and the anion thus generated will add to the gamma keto sulfone and gets protonated to get this molecule. Okay. CO2 SO2pH. Okay, so a Michael addition reaction. And now under basic condition, this SO2pH can eliminate, or in other words, we have introduced the vinyl group here, CO2 and now we need to introduce another vinyl group at here. How? We can use the Grignard reagent, vinyl Grignard reagent. So the Grignard will add here and form this compound. So what will be the product? Benzene ring, this one O minus, okay. And now if you heat this molecule, what can happen? Now this is a 1,5 ketone. It can undergo a Claisen reaction or COP rearrangement, specifically oxy-COP rearrangement to form this product. O minus double bond. Here you have the ester. Okay, and now we can convert this enolate to the keto form, and this is nothing but our product. So by using the knowledge of sigmatropic rearrangement, we have converted a compound to this system via introduction of two vinyl groups. One is electrophilic way of introducing a vinyl group. The second is a nucleophilic way of introducing a vinyl group. And Claisen rearrangement, as you have seen, we know it is a allyl vinyl ketone, allyl vinyl or allyl aryl ether cyclization to form these orthoallylated phenols via a 3,3 sigmatropic rearrangement. And if we have the two ortho position blocked, the first 3,3 sigmatropic rearrangement can take place at the ortho position, and this is followed by a second 3,3 sigmatropic rearrangement to form the para-substituted phenol derivative. So there are some more reactions. I'm not able to cover it, the ene reaction, but that's not very important, I would say. But please remember the classical 3,3 sigmatropic rearrangements, mostly the Claisen rearrangement and the COP rearrangement, and also the first part of our talk on electrocyclic reaction and the cycloaddition reaction. I hope in the last 2 hours, I hope you are not bored. I was able to give you a take-home message on pericyclic reaction. If you have any doubt, feel free to write to me. I hope I will be able to get back to you in 2-3 days. Thank you very much. And once again, thank you very much, Jomo and Tanya, for giving me this opportunity to give some information to the students. And I'm very happy that at least some way I can interact with the students. And thank you very much. And I hope I will be able to physically come to your institute one day. Thank you very much.
It is actually an honor and privilege to have you with us to interact with the students.
Yeah, so if it was like a board and chalk, I hope I will be able to give a better message regarding the cycloaddition reaction. But with this PowerPoint presentation, I don't know how much it was good.
Managed very well. It was very effective.
Students, if you have any specific questions, quickly 1 or 2 questions. If you have any, please, you can use this forum right now to interact, or any comments. I think you had some glimpse of pericyclic chemistry. Your feedback form is also shared. Kindly fill it up so that we can bring up more of these kinds of programs. If there are no more questions, let us conclude this session. So it was a wonderful, again, right from 2 days, we had a wonderful session on aromaticity and how molecular orbital theory was used to explain many concepts. And today we talked about pericyclic. The basics were fully covered. I don't think we have to take anything much. The basics, at least for the degree, it is totally done. For the PG students also, only thing is they might have some correlation diagram left in their studies explaining such things, but otherwise it's all done. And more the beauty was, you have also seen some retrosynthetic analysis, how a complex molecule can be visualized. So I often tell to students, this is organic chemistry is something like you're an engineer, how to build a molecule. If you can visualize, yeah, that's the beauty. So getting up that kind of a molecule from a retro-Diels-Aldol reaction, it's really you need some imaginative skills. And if students are really good at this, you have a lot of scope to work in organic chemistry. You will be a very sought after in industries, in research, and whatever it is. But you really need to get a grip on this. And it was a wonderful session, I would say. And also your drawings were very, very excellent. Many times when you go for some textbooks, you don't see that orbitals that clearly. Students will find it very difficult because even in Claydon or even in this, some figures we cannot just copy. It's difficult. So you have to make your own. Some of them were excellent. I think those slides were very good. Students will be really benefiting out of it, especially today's those FMO approach is fully covered. So I would say this was excellent. We are very grateful to you. Thank you for accepting and being part of this student enrichment program. And we definitely look forward to you. On behalf of all the staff, faculty members and students and all the participants here, we really thank you for your time, your patience, your energy, everything. That's it. Thank you very much.
Please join for the talk tomorrow also.
Yeah, that's one more point. Yes.
I try to give a little flavor about what we are doing.
Research, yes.
Yes. Students, once again, there is a Farouk College. There is a conference going on. Students can still be a participant. Please go there to the Farouk College, which is actually very near to our college. And there is an international conference going on. And Dr. Biju is a keynote speaker there. Please come up there. He's talking on some fantastic whatever work he's doing with organocatalysis and building up some nitrogen-based heterocyclics, I think. That's what the title I saw. So please, students, come and understand that part as well, which will help you. What is the future area? What is the current thing going on in these kinds of organic synthesis? So you can join that. Go to the Farouk College website, Department of Chemistry. There is a conference. Link is given there. You can directly register. You will get the ID, Zoom ID for joining that program. So thank you all once again. Thank you, Dr. Biju.
Thank you. Thank you very much.
Thank you, Biju sir.
Thanks. Thanks. Jomon, thank you very much once again. And,
Yes. Yeah, it was nice to meet you after a long time.
It would be better if you could come personally sometime soon.
Yeah.
Hopefully after the COVID situation is sorted.
Yeah, otherwise I would have been in Calicut today.
Yeah.
For tomorrow, at least you should have been.
Okay, yeah. Okay, then let's wind up.
And